The question of how the universe will end has fascinated humanity for centuries. From ancient myths to modern science, the ultimate fate of everything we know, space, time, matter, and energy, remains one of the greatest mysteries. As we peer deeper into the cosmos, new theories have emerged, painting vivid yet unsettling pictures of how the universe might meet its final chapter. Among these, five major ideas stand out: the Big Freeze, the Big Crunch, the Big Rip, vacuum decay, and heat death. Each presents a unique scenario, governed by the laws of physics and cosmology, and each tells a story of cosmic endings on scales that challenge human imagination. The universe is currently expanding, a discovery confirmed by Edwin Hubble nearly a century ago. But this expansion is not uniform or predictable in a simple way. Observations show that the expansion rate is accelerating, driven by a mysterious force called dark energy, whose nature is still unknown. Depending on how dark energy behaves in the future, the universe's fate could take radically different turns. To understand these endings, it's essential to explore these theories one by one, examining the scientific foundations and implications behind them. The Big Freeze, sometimes called the heat death scenario, is perhaps the most widely accepted theory among cosmologists today. It is based on the idea that the universe will continue expanding forever, but as it does, all sources of energy will gradually be exhausted. Galaxies will drift apart, stars will burn out, and matter itself will grow colder and darker. Eventually, the universe will reach a state of maximum entropy, a condition where no more usable energy exists to do work. In this scenario, life as we know it becomes impossible. The cosmos will become a vast, dark, and frigid expanse. The process leading to the Big Freeze begins with the expansion of space itself. As galaxies move away from each other, the density of matter and radiation drops. Stars form less frequently because the gas clouds needed to birth new stars become too sparse. Existing stars age and die, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Over unimaginably long timescales, even black holes evaporate through a process called Hawking radiation, releasing their energy back into space. With no stars left to shine, the universe will be populated by cold remnants slowly fading away. Entropy, a measure of disorder in a system, drives this process. The second law of thermodynamics dictates that entropy must increase in a closed system. The universe, considered as such, will inevitably become more disordered and less hospitable to structured forms like galaxies, planets, and life. The Big Freeze is the gradual, inevitable march towards this state of maximum entropy and thermal equilibrium. Contrasting the Big Freeze is the theory of the Big Crunch. While the Big Freeze imagines an endlessly expanding universe, the Big Crunch suggests a cyclical fate, where the universe's expansion eventually halts and reverses. In this model, gravity overcomes the outward push of expansion, pulling all matter and energy back together into a contracting cosmos. This process would culminate in a massive collapse, compressing everything into an incredibly dense, hot state, potentially akin to the singularity from which the Big Bang itself emerged. For the Big Crunch to occur, the density of matter and energy in the universe must be high enough to slow and reverse the expansion. This depends heavily on the properties of dark energy and the total mass energy content of the universe. Early cosmologists thought the Big Crunch was likely because gravity seemed strong enough to halt expansion. However, modern observations of accelerated expansion cast doubt on this scenario, making it seem less probable. Still, the Big Crunch remains a compelling idea. It suggests the universe could be cyclic, with phases of expansion and contraction repeating indefinitely. Some theories even propose that after the Big Crunch, a new Big Bang could occur, initiating a fresh cosmic cycle. This idea resonates with certain philosophical and mythological concepts of eternal recurrence and renewal. In summary, the Big Freeze and Big Crunch represent two fundamentally different endings, one where the universe expands forever into cold darkness, and another where it collapses back into a dense singularity. Both have profound implications for the fate of matter, energy, and life. Next, we will explore other dramatic theories that imagine even stranger cosmic finales. The Big Rip, vacuum decay, and the ultimate heat death. These scenarios challenge our understanding of physics and stretch the imagination toward the most extreme possibilities for the end of everything. After exploring the Big Freeze and the Big Crunch, we step into even stranger and more dramatic scenarios that scientists have proposed for the end of the universe. These include the Big Rip, vacuum decay, and a deeper understanding of the heat death, each based on different assumptions about the nature of dark energy, the quantum structure of space, and the laws governing the cosmos. The Big Rip is a scenario born from the idea that dark energy, the mysterious force accelerating the expansion of the universe, might not be constant, but instead grow stronger over time. If this is the case, the expansion would not just continue forever, but would accelerate so wildly that it would eventually overcome all other forces, tearing apart galaxies, stars, planets, and ultimately even the atoms that make up matter itself. In the Big Rip, as dark energy's strength increases, the rate at which space expands grows exponentially. First, galaxy clusters become gravitationally unbound, drifting apart at speeds faster than light. Then individual galaxies cannot hold their stars, and stars lose their grip on planets orbiting them. On progressively smaller scales, molecules, atoms, and subatomic particles are ripped apart, leaving a universe where nothing can stay intact. The timeline for this cosmic destruction depends on the exact properties of dark energy, particularly a parameter called the equation of state. If this parameter falls below a certain threshold, known as the phantom energy regime, the Big Rip becomes inevitable. Current measurements are inconclusive, but the idea remains a fascinating and terrifying possibility, showing how the unknown qualities of dark energy shape cosmic destiny. Vacuum decay, sometimes called a false vacuum collapse, shifts the focus from cosmic expansion to quantum physics and the stability of the vacuum itself, the fundamental state of space. According to quantum field theory, the vacuum is not empty, but filled with fluctuating fields and energies. What we consider the vacuum may be only metastable, meaning it's a local minimum in the energy landscape, but not the absolute lowest state possible. If the vacuum is metastable, a catastrophic transition to a true vacuum state could occur spontaneously or be triggered by an event such as a high-energy cosmic ray collision. This true vacuum would have different physical laws and constants, and a bubble of this vacuum would expand at the speed of light, converting everything in its path into this new state. The consequences of vacuum decay would be instantaneous and irreversible. All matter, forces, and structures would be obliterated or transformed beyond recognition. From our perspective, this event would be the absolute end of the universe as we know it. No gradual fading or collapsing, but an abrupt cosmic reset. The likelihood and timing of such an event remain unknown, but it represents one of the most radical and frightening end-of-universe theories. The final scenario to discuss, often confused with the Big Freeze but more specific, is heat death. This theory focuses on the thermodynamic future of the universe. Heat death describes a state where the universe reaches maximum entropy and thermodynamic equilibrium. This means all energy differences that can be used to do work have been exhausted, and no processes can occur that increase order or complexity. Unlike the Big Freeze, which mainly emphasizes expansion and cooling, heat death zeroes in on the ultimate fate of energy distribution. When the universe reaches this state, everything will be uniformly cold and dark. Stars and galaxies will have ceased all activity, black holes will have evaporated, and even subatomic particles will be so sparse that interactions become impossible. Time itself loses meaning as no change or evolution occurs. The idea of heat death dates back to the 19th century and is deeply rooted in the laws of thermodynamics. It implies a universe that becomes a quiet, still wasteland where life cannot exist. Although it might take unimaginable trillions of years to approach this final state, it represents a sobering vision of cosmic stillness and death. Taken together, these theories, Big Rip, vacuum decay, and heat death, show just how varied and extreme the potential ends of the universe might be. From the slow and steady fading to the abrupt and total annihilation, the cosmos' future depends on deep and unresolved questions about fundamental physics, dark energy, and the structure of reality itself. As science advances and our observations of the universe improve, we may come closer to knowing which of these endings is most likely. Until then, they remind us that the universe is vast and mysterious, governed by forces and phenomena far beyond everyday experience, capable of endings as dramatic as its beginnings. Having explored the 5 major theories that could bring about the end of the universe, the Big Freeze, the Big Crunch, the Big Rip, vacuum decay, and heat death, it's important to reflect on what these scenarios reveal about the cosmos, physics, and even our place in the grand scheme of existence. Each theory is grounded in deep scientific inquiry, relying on observations, mathematical models, and the laws of physics. Yet they also confront us with profound uncertainty. The universe's fate depends heavily on factors we have only begun to understand. The true nature of dark energy, the stability of quantum fields, and the exact makeup of matter and energy on cosmic scales. These unknowns leave open a wide range of possible futures, some gradual and peaceful, others sudden and catastrophic. The Big Freeze and heat death present an image of slow decay and silence. They embody the idea that the universe, having given birth to galaxies, stars, planets, and life, will eventually run out of usable energy. This inexorable increase in entropy leads to a cosmos where change stops and time loses meaning. The philosophical implications are stark. Everything we know, every story ever told, every spark of life, faces a future of fading into oblivion. It is a reminder of the fragility and fleeting nature of existence. In contrast, the Big Crunch and the cyclic universe model offer a vision of renewal. If the cosmos contracts back into a dense state, it might set the stage for another Big Bang, a new beginning. This cyclic view challenges the idea of a one-time creation and end, suggesting instead an eternal rhythm of birth, death, and rebirth. It resonates with ideas found in various cultural and philosophical traditions, linking scientific speculation with human attempts to find meaning in cycles of time. The Big Rip and vacuum decay, meanwhile, highlight the unpredictability and potential violence of the universe's fate. They reveal that the universe's end might come not as a slow fading, but as a sudden and complete transformation or destruction. These scenarios emphasize how much remains mysterious about the forces shaping reality, and how fragile the structures of matter and space might be under extreme conditions. Scientifically, these theories push the boundaries of knowledge. They encourage physicists and cosmologists to develop new models, refine measurements of cosmic parameters, and seek a deeper understanding of dark energy and quantum mechanics. They also remind us that our current theories, while powerful, are provisional and subject to revision as new evidence emerges. From a human perspective, contemplating the end of the universe can evoke a wide range of emotions, from awe at the vastness and complexity of the cosmos to existential anxiety about impermanence. Yet it can also inspire humility and curiosity, motivating us to explore, learn, and appreciate the fleeting beauty of the universe we inhabit. Ultimately, the question of how the universe will end is not just about cosmic destiny, but about the nature of time, space, matter, and life. It invites us to ponder the meaning of existence on the largest scales and the connections between the tiniest particles and the grandest structures. While the end might be distant, billions or trillions of years away, understanding these possibilities enriches our knowledge and imagination. It challenges us to think beyond everyday life and consider the deep mysteries of reality, reminding us that we are part of a vast, dynamic cosmos with a story that continues to unfold. As we continue to study the universe, new discoveries may reveal surprises that alter our understanding of its fate. Until then, the theories of the Big Freeze, Big Crunch, Big Rip, vacuum decay, and heat death stand as powerful narratives of cosmic endings, each a testament to humanity's quest to comprehend the ultimate destiny of everything. If you enjoy this journey space and time possibility, don't forget to like, subscribe, and share. Until next time, till looking up, the universe is waiting.